Hello, welcome back. This is Ken and we're still on our course on mechanics, and this is the second part of lesson 7 on potential energy and energy conservation. In this lesson, we are going to discuss about the elastic potential energy, and in later parts of this video, we are going to have an example on the conservation of energy wherein you have your kinetic energy, your gravitational potential energy, and your elastic potential energy involved in your problems. Now, as you can remember, in the past lessons, we have already discussed the work done by a spring, and the work done by a spring that is equal to your work elastic is equal to 1 half kx1 squared minus 1 half kx2 squared, where again here your k is your spring constant, your x1 is your position at, or is your position at point 1, and your x2 is the position at point 2. So again, your work elastic for the work done by a spring is equal to 1 half kx1 squared minus 1 half kx2 squared. And in figure A, you have here, just for your reference, in figure A, you have there your equilibrium position for your system. This is when your spring is neither stretched nor compressed. So we take here your x equals 0 at your origin to be your equilibrium position. And in figure B, as the spring stretches, okay, you stretch the spring to the positive x-axis, it does a negative work on the block. So again, you have here a negative work done because we have here a negative work done because again your displacement is towards this direction, while the force of the spring is towards the opposite direction. You have your restoring force, if you can remember. And as the spring relaxes, it does a positive work on the block. That is when a compressed spring, or that is when you let the block, or you let go of the spring. So the spring does a restoring force on your block or on your system. And when you have a compressed spring, it does a positive work on the block as it relaxes, because this time here you have your displacement there, so it now moves to your left, and the force of the spring also goes there. Okay, so you have here again the work done by a spring. So again, this is different when we're going to talk about the work done on a spring, because when you have a work done on a spring, you have your 1 half kx2 squared minus 1 half kx1 squared. This is available on, or the discussion about this is again available on lecture 6 of this course. So this is the work done on a spring. Now, the elastic potential energy. Body is elastic if it returns to its original shape after being deformed. Like say, for example, your spring. So your spring then does contain a elastic potential energy, because when you are going to deform the spring by either stretching it or compressing it, your spring returns to its original shape. Elastic potential energy is the energy stored in an elastic body such as a spring, but you have, of course, other elastic bodies, like say, for example, your rubber or even your skin. It's elastic. So when you're going to stretch your skin, it returns to its original shape once you let go of the stretching force. The elastic potential energy stored in an ideal spring is equal to your 1 half kx squared. So this is your elastic potential energy. So we now have three energies. You have your kinetic energy, which is 1 half mv squared, and we have your gravitational potential energy, U graph that is equal to mg y. And now we have your elastic potential energy, which is equal to 1/2 k x squared. Okay. The figure at the right shows a graph of the elastic potential energy for an ideal spring. So when you, or along the x-axis, that is your relative position with stretching and compression. And on your y-axis is the elastic potential energy. So you have here a parabola for the graph of your elastic potential energy. So at maximum compression at x at this point here at the negative x-axis, you have here your maximum elastic potential energy. And as you let go of the compression, it returns to the equilibrium position wherein there is any more, or there is no elastic potential energy anymore stored. But when you are going to stretch the spring, as you stretch your spring, the elastic potential energy increases, like this one here. Now, there are actually situations wherein both your gravitational and your elastic forces are present. Like, say, for example, we have here a trampoline. Okay, when you're going to play with a trampoline by jumping on it, you're stretching the trampoline. But you observe that once you stretch the trampoline returns to its original shape. Thus, your trampoline is an elastic body. So, when you're going to jump on it, you feel this force that the trampoline is exerting on you. That is why you move high up the ground. So in this situation, you have both your elastic forces, which is the force applied by the trampoline on you, and when you are high up the ground, you have uh, your gravitational force. So for this situation here, both your elastic and then your gravitational force is present. And when a situation involves both gravitational and elastic forces present, the total potential energy is just the sum of the gravitational potential energy and the elastic potential energy. That is your total potential energy U is equal to your U gravity plus your U elastic. If then other forces act on the body in addition to its weight, so we have here, for the situation with both gravitational and elastic forces, your work total now becomes your work gravity plus your work elastic plus your work other. If gravity is the only force that acts, and of course you have your elastic potential, so we can, just like we did, what we did in the previous lecture, so we can equate this one to your work kinetic energy theorem, your K2 minus K1. So we then now have your work other plus your work elastic plus your work gravity. That is equal to your K2 minus K1. Playing with the equation, we get this final form here. You have your K1 plus U grav 1 plus U elastic 1 plus work other. This is equal to K2 plus U grav 2 plus U elastic 2. Now then, the work done by all forces other than the gravitational force or elastic force equals the change in the total mechanical energy of the system. You have your total mechanical energy of the system, E is equal to K plus U, where here your U is just the sum of your gravitational potential energy and then your elastic potential energy. We're going to use this one later in examples. So remember here that this is your, on the side here, this is your E1, and on the side here, this is your E2. So we just actually added some terms to make a final form. We have K1 plus U grab plus U elastic 1 plus work other, and then on the side here, you have K2 plus U grab 2 plus your U elastic 2. This is easy to remember, so take note of this one. So let us have an example. This is motions with elastic potential energy. A glider with mass 0.200 kilograms sits on a frictionless horizontal air track connected to a spring with a force constant of K is equal to 5 Newton per meter. You pull on the glider stretching the spring 0.100 meters, and then released it from rest. The glider moves back towards its equilibrium position at x equals 0. What is the x velocity when x is equal to 0.080 meters? So let's read again the problem. You have a glider with mass 0.200 kilograms. So this one here. Uh, a mass is connected to a spring, and this mass here has a mass of 0.200 kilograms. So you have the mass of 0.200 kilograms. This sits on a frictionless horizontal air track connected to a spring with a force constant of K is equal to 5 newtons per meter. So your K, your spring constant, is 5 newtons per meter. You pull in the glider, stretching the spring 0.100 meters, and then release it from rest. So you stretch your spring with the mass on it at some x is equal to 0.01 meters. So this one here, we're referring to this x here, this displacement here. Okay, so that is 0.100 meters. This is your initial condition. You have a stretch spring with a mass on it. So let's call this one as your, let's just call this one as your activity 1. Okay, and then you release it from rest. Okay, after stretching it at some time, you release it from rest. Okay, so the glider moves back towards its equilibrium position as always because of the restoring force of the spring. What is its x velocity when x is equal to 0.080 meters? So when it returns to its original position, we are as of this point here. That is when x is equal to 0.080 meters. So we call this one as your event 2 or your activity 2. Okay. Here we're asked for the velocity at this point here. So your velocity 2 at point 2 or activity 2. So here we have your initial velocity v1 is 0 because you have here that you released it from rest. So at point 1, the velocity of your system is 0. So at point 1 also, we have your x1, which is equal to 0.100 meters. The initial position or the position of your glider at point 1. Okay. And at activity 2 at point 2, you have the position x2, which is equal to 0.080 meters. So please take note of this event and of this situation. If you need more time, please pause the video to analyze the problem. Okay, so let's solve the problem. So we have already the given on the previous slide, and we're going to solve the problem now here. Now to solve the problem, you just need to use your energy conservation theorem. So here we have your energy conservation theorem. We just use the general form. You have your E1 is equal to your E2. Again, here this is your event 1, and then here this is your event 2. This is just equal to your K1 plus your U. Grab 1, let's write everything, plus U elastic 1 plus work other. This is equal to your K2 plus U grav 2 plus U elastic 2. But here, this is just at the horizontal. So that means we do not need these terms. We do not need your gravitational potential energy terms. So we just have your K1. And by the way, since this is a horizontal or a frictionless surface, horizontal frictionless surface, so this is frictionless, we do not also have some or other. So what we are left with your equation is you have your K1 plus your U elastic 1. This is equal to K2 plus U elastic 2. Okay, but at event 1 here, your velocity 1 is 0. So let's just write everything. So from this equation, here, you have your 1 half mv1 squared plus 1 half kx1 squared. This is equal to 1 half mv2 squared plus 1 half kx2 squared. At event 1, your velocity is 0. So this is just 0. So we are now left with just 3 equations. And here, our target is to solve for the velocity 2 when your x is at 0.080 meters. So this one here is our target variable. Let's just solve this one individually. So you have your U elastic 1. Sorry, let me just erase this one. Let me erase these terms here. So we have first, your K1 again is 0. And we now solve for your U elastic 1. So you have your 1 half 5 newtons per meter, that is your K, times 0.100 meters, and then you square it. So this is equal to 0.0250 joules. So your K2, this is 1 half mv2 squared. Our target is your V2, so we cannot get here yet your kinetic energy 2. Your U elastic 2, this is equal to your 1 half 5 newtons per meter times 0.080 meters squared. So we have here 0.0160 joules. 0.0160 joules. Okay, so here we have now, let's go back here. So you have here 0.0250 joules. This is equal to 1 half mv2 squared plus 0.0160 joules. We need to solve for your V2. So we have 0.0250 joules minus 0.0160 joules. And then this is equal to 1 half mv2 squared. So you multiply this one by 2. Multiply both sides by 2 so that your 2 cancels out here, and then you divide by m so that here your mass cancels out, and then you get the square root of this one here to get your V2. And take note here that this one here is a positive and a negative root, but we're going to use, or we're going to get the negative V2 because here your glider moves to the left. So here your V2 should be negative. So the roots of this one are, you can solve this one, and the roots of this one is equal to, or the roots are positive, negative, uh, 0.30 meters per second. But again, we are going to use the negative root because it moves to the left. So thus here, your V2 is equal to negative 0.30 meters per second. If instead that your glider moves to the right, we use the positive root of your answer.